In the twilight years of the Cold War, a phantom emerged from the shadows of the United States' most secretive aircraft development programs. The Northrop McDonnell Douglas YF-23 was not just another fighter jet. It was a glimpse into the future of aerial warfare, a revolution in stealth technology that pushed the boundaries of what was thought possible in military aviation. Born from the United States Air Force's Advanced Tactical Fighter program, the YF-23 was designed to outmaneuver, outrun, and outfight any threat in the skies. Its alien-like appearance, with a 43-foot 7-inch diamond-shaped wingspan and saw-toothed exhaust nozzles, wasn't just for show. Every curve, every angle of its muscular 67-foot 5-inch frame was meticulously crafted to achieve unprecedented levels of stealth, making it virtually invisible to enemy radar. But invisibility was just the beginning. Twin state-of-the-art turbofans propelled the YF-23 to blistering speeds with 35,000 pounds of thrust, pushing the aircraft beyond Mach 2. More impressively, it could supercruise, flying supersonic without afterburners, at speeds exceeding Mach 1.6. Its advanced avionics and sensor fusion capabilities, housed within a state-of-the-art cockpit with a 360-degree view, aimed to give pilots an almost superhuman awareness of the battle space around them. The YF-23 would go head-to-head with the Lockheed Martin F-22 Raptor in a fiercely fought competition for the Air Force contract, resulting in a controversial decision that continues to be the source of heated debate over 30 years later. The story of the YF-23 began in the early 1980s, amidst growing concerns within the United States Air Force about the capabilities of new Soviet fighters. The introduction of the Mikoyan MiG-29 Fulcrum and Sukhoi Su-27 flanker posed a significant threat to the United States' aerial dominance, potentially outclassing even the formidable F-15 Eagle. This perceived vulnerability spurred the Air Force to initiate the Advanced Tactical Fighter, or ATF program, in 1981, seeking a next-generation aircraft that could maintain the United States' edge in any potential conflict. The ATF program demanded a quantum leap in fighter technology. The new aircraft would need to incorporate stealth capabilities, supercruise, the ability to sustain supersonic flight without afterburners, and advanced avionics, all while maintaining the agility necessary for air-to-air combat. These requirements pushed the boundaries of what was technologically possible at the time, challenging America's aerospace industry to innovate like never before. Northrop, a company with a rich history in aviation, recognized the opportunity to shape the future of aerial warfare. Partnering with McDonnell Douglas, they assembled a team of the industry's brightest minds to tackle the ATF challenge. Leading this effort was Northrop's ATF program manager, Del Jacobs, who coordinated the work of thousands of engineers and scientists across 30 states. The development process was shrouded in secrecy, befitting the classified nature of the project. The team worked in a windowless, unmarked building on Northrop's campus, with security measures so strict that employees had to park their cars at a distance to avoid detection by Soviet spy satellites. This clandestine environment, coupled with the project's ambitious goals, fostered a sense of urgency and innovation among the staff, who often worked 14-hour days, 7 days a week. As the 1980s progressed, the Northrop McDonnell Douglas team refined their design, leveraging advanced computer simulations and wind tunnel testing. By 1986, their concept had evolved into a unique and promising configuration that would become the YF-23. In October of that year, the Air Force selected Northrop and Lockheed as the two finalists in the ATF competition. Each company was tasked with building two prototype aircraft for evaluation. Northrop's team redoubled their efforts, working tirelessly to transform their design into reality. The YF-23's design was a harmonious blend of stealth and aerodynamic efficiency, representing a significant leap forward in fighter aircraft technology. The fuselage was sleek and elongated, stretching approximately 67 feet 5 inches in length. It featured smooth, blended contours that minimized radar reflections while efficiently managing airflow. The forward section featured a modified double trapezoid cross-section, transitioning seamlessly into a circular profile towards the rear. This careful shaping not only enhanced the aircraft's stealth characteristics, but also reduced transonic and supersonic drag, enabling the YF-23 to achieve remarkable speed and range. Despite its considerable size, the YF-23 maintained a relatively low empty weight of approximately 29,000 pounds, thanks to the extensive use of composite materials and advanced manufacturing techniques. However, its most striking feature was undoubtedly the unconventional diamond-shaped wing planform. Spanning 43 feet 7 inches, the diamond shape offered superior aerodynamic performance across a wide range of speeds compared to traditional swept wings. The leading edge was swept at 40 degrees, while the trailing edge had a forward sweep of 55 degrees. This configuration provided excellent lift characteristics and reduced drag at high speeds, contributing to the aircraft's supercruise capability. The wing design also incorporated advanced airfoils that maintained laminar flow over a larger portion of the wing surface, further reducing drag. The wings were also equipped with leading-edge flaps and trailing-edge elevons. These worked in conjunction with the distinctive V-tail at the rear of the aircraft, which replaced conventional vertical and horizontal stabilizers to provide precise control in all flight regimes. The V-tail surfaces were canted outward at approximately 50 degrees from vertical. This design choice served multiple purposes. It reduced the aircraft's radar signature by eliminating the right-angle intersections typical of conventional tails, improved stability at high speeds, and contributed to the YF-23's impressive maneuverability. The all-moving tail surfaces, dubbed ruddervators, provided precise control in all flight regimes. They could move independently or in concert to generate pitch, yaw, and roll moments. This innovative control scheme allowed for exceptional agility without compromising the aircraft's stealth characteristics. Powering the YF-23 were two advanced turbofan engines housed in nacelles on either side of the aircraft's spine. These nacelles, larger than what would have been used in a production model, were designed to accommodate potential thrust reversers, a feature later deemed unnecessary. The engines were fed by innovative S-shaped air inlets, which shielded the engine faces from radar waves, further enhancing the aircraft's stealth properties. Each of the two prototypes featured a different engine configuration. One was equipped with Pratt & Whitney YF-119 engines. This engine, which would later be selected for the F-22 Raptor, was a high-thrust, low-bypass turbofan capable of producing approximately 35,000 pounds of thrust with afterburner. Meanwhile, the other prototype utilized the more advanced General Electric YF-120 variable cycle engine, which could adjust its bypass ratio for optimal performance at different flight regimes. Both power plants were cutting-edge designs, enabling the YF-23 to achieve supercruise speeds in excess of Mach 1.6 without afterburners. One of the most innovative features of the YF-23's propulsion system was its exhaust design. Instead of traditional round nozzles, the YF-23 employed two-dimensional, letterbox-shaped exhaust ports. These were integrated into troughs on the upper surface of the aircraft, lined with heat-dissipating tiles similar to those used on the space shuttle. This configuration significantly reduced the aircraft's infrared signature, making it less vulnerable to heat-seeking missiles. Another cornerstone of the YF-23's design was its stealth capabilities. Every aspect of the aircraft was shaped to minimize radar reflections and reduce its overall radar cross-section. The blended wing body design eliminated many of the right angles and sharp edges that typically contribute to an aircraft's radar signature. The YF-23's stealth properties were further enhanced by the use of radar-absorbing materials. These materials were applied to key areas of the airframe, absorbing incoming radar waves rather than reflecting them back to the source. The exact composition of these materials remains classified, but they likely included ferrite-based compounds and carbon-impregnated materials. The aircraft's sensor and avionics apertures were carefully designed to maintain the low observable profile. Antennas and other necessary protrusions were either recessed or covered with radar-transparent materials to prevent them from compromising the aircraft's stealth. The YF-23's weapons were to be carried internally in weapons bays to maintain its stealth profile during combat operations. While the prototype aircraft were not equipped with operational weapons systems, the design included provisions for multiple internal bays capable of carrying a variety of air-to-air missiles and possibly air-to-ground ordnance. In the cockpit, the YF-23 featured state-of-the-art avionics and a sophisticated fly-by-wire system. The pilot's station was positioned high in the nose, offering excellent visibility. The cockpit was designed with a large single-piece canopy that provided an unobstructed 360-degree view, crucial for situational awareness in air combat scenarios. The fly-by-wire system was a quadruple redundant digital flight control system that translated pilot inputs into precise control surface movements. This system allowed for exceptional maneuverability and stability across the aircraft's entire flight envelope, from low-speed, high-angle of attack flight to supersonic cruise. While the prototypes were not equipped with full combat systems, they were designed to accommodate advanced sensor suites and electronic warfare systems. The production version was expected to include an active electronically scanned array radar, infrared search and track system, and a comprehensive electronic warfare suite. The first YF-23 prototype PAVE-1 was rolled out on June 22, 1990. It was informally known as Spider or Black Widow 2 due to the red hourglass shape that was originally painted on its ram air scoop to prevent injury to ground crew, which resembled the markings on a Black Widow Spider's belly. The nickname also suggested that it was the successor to the World War II-era Northrop P-61 Black Widow. On August 27th, it took to the skies from Edwards Air Force Base with Northrop test pilot Paul Metz at the controls. The 50-minute maiden flight marked the beginning of an intensive testing program that would push the aircraft to its limits and beyond. On October 26, the second prototype, PAV-2, nicknamed the Gray Ghost, was flown for the first time by Jim Sandberg. Over the next several months, both YF-23 prototypes underwent rigorous flight testing. Both aircraft demonstrated exceptional performance, achieving super cruise speeds of Mach 1.43 in the Pratt and Whitney YF-119 powered PAV-1 and an impressive Mach 1.6 in the General Electric YF-120 equipped PAV-2. The YF-23's high-speed capabilities and superior stealth characteristics seemed to position it favorably in the competition against Lockheed's YF-22. The testing phase revealed the YF-23's exceptional stability and control characteristics. Test pilots reported that the aircraft was highly responsive and easy to handle, even at high speeds and altitudes. The innovative V-tail configuration proved effective in providing precise control without compromising stealth. During high angle of attack testing, the YF-23 demonstrated the ability to maintain controlled flight at angles up to 60 degrees, showcasing its potential effectiveness in close-range air combat scenarios. The aircraft's thrust-to-weight ratio and low wing loading contributed to its impressive climb rates and sustained turn performance. However, the competition was far from one-sided. While the YF-23 excelled in speed and stealth, the YF-22 demonstrated superior agility, particularly in low-speed, high-angle of attack maneuvers. This disparity would prove crucial in the Air Force's final evaluation. Throughout the testing phase, the Northrop team continued to refine the YF-23's design, addressing minor issues and optimizing its performance. The aircraft's fly-by-wire system was fine-tuned to enhance its handling characteristics, while its stealth features were continuously evaluated and improved. Despite the YF-23's impressive capabilities, the Air Force announced in April 1991 that it had selected the Lockheed YF-22 as the winner of the ATF competition. The decision came as a blow to the Northrop team, who had poured years of effort and innovation into their design. Several factors contributed to the YF-22's selection. Its superior agility was seen as a critical advantage in close-range air combat. Additionally, the Air Force perceived the YF-22 as a less risky option, with a more conventional design that was closer to existing fighter aircraft. There were also considerations beyond pure performance, including assessments of production readiness and long-term development potential. With the competition's conclusion, the two YF-23 prototypes were retired. The project that had once consumed the efforts of thousands of engineers and technicians across the country came to an abrupt end. The aircraft that had pushed the boundaries of stealth and speed would never see production or combat service. Several decades later, discussion continues to abound about whether the correct decision was made. Although the YF-23 never entered production, its impact on aviation technology and fighter design has been significant and lasting. The advanced stealth techniques developed for the YF-23, believed by many to have been superior to those of the F-22, have influenced subsequent aircraft designs, contributing to the evolution of low observable technology. The The YF-23's innovative aerodynamics, particularly its diamond-shaped wing and V-tail configuration, demonstrated new possibilities in aircraft design. These concepts have informed the development of other advanced aircraft, pushing the boundaries of what is possible in terms of speed, maneuverability, and stealth. The advancements in the propulsion system, especially the integration of engines for reduced infrared signature, have had lasting impacts on military aviation. The supercruise capability, once a novel concept, has become a standard feature in fifth-generation fighters. The YF-23's fly-by-wire system and advanced cockpit design laid the groundwork for future developments in aircraft control and pilot interface. The emphasis on sensor fusion and integrated avionics has become a hallmark of modern fighter aircraft design. Today, the two YF-23 prototypes serve as reminders of this remarkable chapter in aviation history. One aircraft is displayed at the National Museum of the United States Air Force in Dayton, Ohio, while the other resides at the Western Museum of Flight in Torrance, California. These preserved examples continue to inspire engineers, aviation enthusiasts, and the public, showcasing the cutting-edge technology and bold innovation that characterize the Advanced Tactical Fighter program. The YF-23 stands as a testament to American aerospace ingenuity. While it may not have won the ATF competition, its legacy lives on in the advancements it pioneered and the boundaries it pushed. In the annals of aviation history, the YF-23 remains a symbol of the relentless pursuit of technological excellence and the endless quest for air superiority. The Boeing B-47 Stratojet was the world's first swept-wing bomber, a pioneer that revolutionized aviation design. When it first took to the skies in 1947, it looked like nothing else on Earth. With its 6 engines suspended under razor-thin wings, it seemed to have arrived from the future. The B-47 was not just a looker, it was also blindingly fast. In 1949, it smashed the cross-country speed record, flying from Washington State to Washington, D.C., averaging over 600 miles per hour, faster than any previous bomber could dream of flying. This extraordinary aircraft played a crucial role during one of the most dangerous moments in human history. During the Cuban Missile Crisis of 1962, B-47 reconnaissance variants assisted U-2 spy planes in providing photographic evidence of Soviet missiles in Cuba, directly influencing President Kennedy's decisions as the world teetered on the brink of nuclear war. The B-47's innovations weren't confined to military use. Its revolutionary design, those swept wings and podded engines, became the template for virtually every large jet aircraft that followed, including the Boeing 707 that ushered in the age of mass air travel. From its record-breaking speeds to its Cold War espionage, from its nuclear deterrence role to its lasting impact on commercial aviation, the B-47 Stratojet didn't just push the boundaries of flight, it redefined them entirely. Even as World War II raged on, American military strategists were already looking beyond the current conflict. In June 1943, with the outcome of the war still uncertain, the United States Army Air Forces, or USAAF, took a bold step towards the future of aerial warfare. Aircraft manufacturers received an informal inquiry from the USAAF to explore designs for multi-jet planes. The focus was on developing aircraft suitable for swift reconnaissance photography or medium-range bombing missions. This forward-thinking initiative aimed to create an aircraft that could outpace enemy interceptors and penetrate deep into hostile territory. At the time, the backbone of America's bomber fleet consisted of propeller-driven aircraft like the B-17 Flying Fortress and the newly introduced B-29 Superfortress. While formidable, these aircraft were approaching the limits of their performance capabilities. The emerging jet engine technology promised speeds and altitudes far beyond what propeller aircraft could achieve, but it also presented new engineering challenges. On November 17, 1944, the USAAF solidified its vision by issuing formal requirements for a jet-powered medium bomber. The project's requirements were notably demanding. The proposed aircraft needed to cover vast distances, operate at extreme altitudes, and achieve remarkable speeds. Specifically, it was expected to fly 3,500 miles without refueling, reach heights of 45,000 feet, and travel at speeds up to 550 miles per hour. This set off a fierce competition among America's leading aircraft manufacturers, including Boeing, North American Aviation, Convair, and Martin. The initial concepts for jet bombers were essentially adaptations of existing designs. Boeing's first study, known as the Model 424, was little more than a scaled-down B-29 with 4 jet engines. Their next iteration, the Model 432, featured 4 engines buried inside the fuselage, fed by intakes beside the cockpit. While innovative, these designs still clung to many conventional bomber design principles. The true breakthrough came in May 1945, just as World War II was ending in Europe. A team of American scientists and engineers, including Boeing's chief aerodynamicist George Schirrer, visited Germany to examine captured aeronautical research. What they discovered would change the course of aviation history. Schirrer encountered German research on swept wings, a concept that promised to dramatically reduce drag at high subsonic speeds. Excited by the potential, he immediately sent a message back to Boeing's design team in Seattle that simply said, quote, "Stop the bomber design." This laconic directive set in motion a complete redesign of what would become the B-47. As World War II came to an end, the urgency for this new type of aircraft intensified. The advent of nuclear weapons had fundamentally altered the nature of warfare, and tensions with the Soviet Union were rapidly escalating into what would become known as the Cold War. The USAAF, soon to become the independent United States Air Force, recognized an urgent need for an aircraft that could deliver nuclear payloads over vast distances with speed and precision. Boeing's design team, led by George Schirrer and Ed Wells, worked feverishly to incorporate the swept wing concept into their bomber design. The result was the Model 450, which featured a 35-degree wing sweep, 6 jet engines mounted in pods beneath the wings, and a sleek, streamlined fuselage. The USAF was sufficiently impressed with this radical design to award Boeing a contract for 2 prototypes, designated XB-47, in April 1946. Just 16 months later, on September 12, 1947, the first XB-47 rolled out of the factory. The most striking feature of the XB-47 was its 35-degree swept wings. This radical departure from conventional straight wings was not merely aesthetic, it served a crucial aerodynamic purpose. The sweep angle was designed to delay the onset of shock waves as the aircraft approached the speed of sound, theoretically allowing the XB-47 to fly at much higher speeds than its straight-winged contemporaries. The wings were also incredibly thin and flexible, a design choice that initially concerned test pilots. However, this flexibility would later prove to improve the aircraft's ride in turbulence and increase its structural efficiency. Another revolutionary aspect of the XB-47's design was its engine configuration. The prototype was powered by 6 General Electric J35 turbojet engines, mounted in pods beneath the wings, 4 in 2 twin-pod arrangements near the fuselage, and 2 in single pods near the wingtips. Considerably different from most contemporary designs, this configuration simplified engine maintenance as the pods could be easily accessed. It also kept the wings free of complex ducting, allowing for a simpler, lighter wing structure. Additionally, spreading the engines along the wingspan saved some structural weight by reducing the bending moment at the wing root. What's more, the XB-47's landing gear configuration was unlike anything seen before on a large aircraft. To accommodate the large bomb bay and the thin wings, Boeing engineers developed a tandem bicycle landing gear arrangement. 2 sets of dual wheels were placed in line along the fuselage centerline, with small outrigger wheels retracting into the inboard engine pods for stability. This unusual setup required a special takeoff technique. The aircraft was built to rest on the ground at the proper takeoff attitude, eliminating the need for rotation during takeoff. The XB-47 was designed with a 3-person crew: pilot, co-pilot, and bombardier navigator. The pilot and co-pilot sat in a fighter-style tandem arrangement under a bubble canopy, while the bombardier navigator was stationed in a compartment in the nose, with windows for visual bombing. Compared to the heavily armed bombers of World War II, the XB-47's defenses were rather minimal. The prototype was designed to feature two .50 caliber machine guns in the tail, though these were not installed for initial flight testing. This reflected a new philosophy in bomber design that prioritized speed and altitude over armament, believing that the best defense was to avoid interception altogether. On December 17, 1947, exactly 44 years after the Wright brothers' first flight, the XB-47 thundered down the runway at Boeing Field in Seattle. Pilots Bob Robbins and Scott Osler guided the sleek silver aircraft into the air for the first time. For 27 minutes, the prototype cruised over Washington state before touching down at Moses Lake Airfield. While this maiden flight was a success, subsequent tests revealed challenges inherent to the B-47's revolutionary design. The aircraft wobbled in a Dutch roll, yawing and rolling in an oscillating dance. At high speeds, the ailerons twisted the flexible wings instead of rolling the aircraft, a phenomenon dubbed aileron reversal. Boeing's engineers tackled these issues head-on. They developed a yaw damper system to counteract the Dutch roll and added vortex generators to the wings to improve airflow. By 1949, these modifications had transformed the XB-47 into a stable, controllable aircraft. In June 1950, the first production model, the B-47A, rolled off the assembly line at Boeing's Wichita plant. The B-47A featured more powerful General Electric J-47GE-11 engines, each producing 5,200 pounds of thrust, a significant improvement over the prototype's J-35 engines. It also introduced a framed canopy replacing the XB-47's bubble canopy and a pair of 20mm M24 cannons in the tail with an A2 fire control system. In addition, it featured the K2 bombing navigation system, significantly enhancing its operational capabilities. However, only 10 B-47As were built. These aircraft served primarily as test beds, allowing the Strategic Air Command, or SAC, to develop tactics and procedures for jet bomber operations. In 1950, while the B-47A was still in its limited production run, Boeing initiated the YB-47C project. This variant aimed to replace the B-47's 6J-47 engines with 4 Wright T-35 turboprops. However, development issues with the T-35 engine would eventually lead to the project's cancellation in December 1952. In 1951, the B-47B made its debut, marking the Stratojet's transition from experimental aircraft to frontline bomber. This version featured more powerful J-47 GE-23 engines capable of producing up to 5,800 pounds of thrust each. The B-47B also introduced the capability for air-to-air refueling, drastically extending its range. A total of 399 B-47Bs were produced. As B-47Bs entered service, Boeing continued to explore alternative propulsion systems. The XB-47D program began, converting 2 B-47Bs to carry a pair of Allison XT-38A2 turboprops in place of the inboard jet engines. While this variant didn't enter production, it provided valuable data on the feasibility of turboprop-powered bombers. In 1953, the B-47B underwent significant improvements under the Ebb Tide program. This initiative saw the addition of ejection seats, enhancing crew safety. The program also introduced a more reliable bombing and navigation system, improving mission effectiveness. External fuel tanks, each holding 1,780 gallons, were added to increase its range further. The same year, Boeing unveiled the B-47E, the definitive version of the Stratojet. This model featured uprated J-47GE-25 engines with water injection, providing a crucial boost of power during takeoff. The water injection system increased thrust by about 10% for takeoff and could be used for about 2.5 minutes before the water supply was exhausted. The E model also boasted a larger fuel capacity of 14,610 U.S. gallons and an improved electrical system. The B-47E was equipped with an A5 fire control system and armed with two 20mm M24A1 autocannons with 350 rounds of ammunition each in the tail turret. A notable sub-variant was the B-47E4, featuring a strengthened landing gear, airframe reinforcement, and greater fuel capacity. Its maximum takeoff weight was increased to 230,000 pounds, and it could carry up to 25,000 pounds of nuclear weapons in its bomb bay. The B-47E's enhanced capabilities made it the backbone of SAC's medium bomber force. Over 1,341 B-47Es were produced, forming a formidable deterrent against Soviet aggression. This included specialized variants such as the EB-47E electronic countermeasures aircraft and the RB-47E reconnaissance variant. As B-47s populated SAC bases across the United States and at forward locations worldwide between 1953 and 1957, the aircraft underwent further modifications. The milk bottle program replaced key wing fittings, further enhancing the B-47's durability and addressing structural fatigue issues identified during operational use. During this period, reconnaissance variants, designated RB-47, joined the fleet. These aircraft, stripped of bombing equipment and bristling with cameras and electronic surveillance gear, probed the edges of Soviet airspace. Their missions were dangerous. Several RB-47s were shot down by Soviet fighters, but the intelligence they gathered was invaluable. In 1956, the B-47's capabilities were put to the test in one of the most daring reconnaissance operations of the Cold War. Codenamed Operation Home Run, this mission saw a fleet of RB-47 reconnaissance aircraft conduct deep penetration overflights of the Soviet Union. Taking off from Thule Air Base in Greenland, these aircraft crossed the forbidding Arctic to gather vital intelligence on Soviet air defense systems, missile sites, and other military installations. However, not all the B-47 operations ran smoothly. During a training mission on March 10th, a B-47 accidentally dropped a Mark VI nuclear bomb near Tybee Island off the coast of South Carolina. Fortunately, the bomb was not armed and did not detonate. While this specific incident was a one-off for the B-47, it highlighted the risks associated with nuclear-armed aircraft during the Cold War era. Meanwhile, as its service career progressed, the B-47 continued to evolve. The TB-47E served as a training aircraft, while the ETB-47E was used for combat crew training. The DB-47E was modified to control QB-47 target drones, showcasing the versatility of the Stratojet design. By the mid-1950s, the B-47 had truly come into its own, proving to be a remarkable aircraft that pushed the boundaries of aviation technology and played a crucial role in shaping Cold War strategy. However, perhaps the Stratojet's finest hour would come in 1962. On October 15th, as Cold War tensions between the United States and the Soviet Union reached a boiling point, reconnaissance aircraft, including RB-47s, intensified their surveillance of Cuba. While U-2 spy planes provided the primary photographic evidence, RB-47s played a crucial support role in gathering intelligence. The discovery of Soviet medium-range ballistic missiles being installed on Cuban soil sent shockwaves through Washington. These weapons were capable of striking most of the continental United States. Over the next 13 days, as President Kennedy and his advisors grappled with the crisis, B-47s maintained a constant presence in the skies. Reconnaissance variants conducted daily overflights, monitoring the buildup of Soviet forces. Bomber variants stood on high alert, engines idling on runways across the United States, crews ready to scramble at a moment's notice. The presence of these aircraft, along with other elements of American military might, sent a clear message to Soviet leader Nikita Khrushchev. On October 28th, Khrushchev announced that the Soviet Union would withdraw its missiles from Cuba. Without dropping a single bomb, the B-47 had played its part in pulling the world back from the brink of nuclear catastrophe. While the B-47 didn't see combat in the Vietnam War, it continued to serve in reconnaissance and support roles during this period, further demonstrating its versatility and enduring value to the Air Force before eventually being retired in 1977. However, the B-47 Stratojet would leave a legacy that extended far beyond its military service. Its revolutionary design, featuring swept wings and pod-mounted engines, became the template for virtually all large jet aircraft that followed. This DNA is evident in everything from modern airliners to military transports, with the Boeing 707, the aircraft that ushered in the age of commercial jet travel, owing much of its design to the Stratojet. Today, aviation enthusiasts can still admire this groundbreaking aircraft in person. While no B-47s remain in flying condition, several examples are preserved in museums across the United States, including the National Museum of the United States Air Force in Dayton, Ohio, the Strategic Air Command and Aerospace Museum near Ashland, Nebraska, and the Castle Air Museum in Atwater, California. These carefully maintained aircraft serve as tangible reminders of the B-47's crucial role in aviation history and its enduring impact on aircraft design. The North American X-15 stands as a towering achievement in the chronicles of aerospace innovation, embodying the relentless quest for speed and the daring spirit of exploration that would take it to the edge of space. Emerging in the late 1950s as Cold War tensions drove the United States' thirst for technology, this sleek, rocket-powered pioneer set new benchmarks in aviation, reaching dizzying altitudes of over 350,000 feet and speeds of Mach 6.7, a record that has not been broken to this day. But this extraordinary aircraft was not just about raw power. It was a sophisticated machine, its resilient Inconel X alloy and innovative control systems specially designed to withstand the intense heat and stress of its high-speed missions. As one of the first reusable aircraft capable of reaching the outer limits of Earth's atmosphere, the X-15 provided invaluable data on hypersonic flight, re-entry, and high-altitude operations, paving the way for future space endeavors including the Space Shuttle. Piloted by some of the most skilled aviators in history, including Neil Armstrong and Pete Knight, the X-15 program was a testament to human ingenuity. The concept for the X-15 originated from an early 1950s study by Walter Dornberger, a German engineer instrumental in the V-2 rocket program who had been recruited by the United States after World War II. Dornberger came up with a proposal for a hypersonic research aircraft capable of reaching unprecedented speeds and altitudes, providing crucial data on aerodynamics, propulsion, and the effects of high-speed flight on structures and pilots. With Cold War tensions continuing to escalate, this idea was of great interest to the National Advisory Committee for Aeronautics, or NACA, the forerunner of NASA, who saw the need for a cutting-edge research platform to push the frontiers of aerospace innovation and inform the design of future spacecraft and high-speed aircraft, thus keeping the U.S. one step ahead of their Soviet rivals in the bitter race for increasingly more advanced technology. To bring this vision to reality, NACA issued requests for proposals in late 1954 and early 1955, inviting aerospace companies to submit designs for both the airframe and the rocket engine. With a reputation for creativity and experience with high-speed aircraft, North American Aviation was selected to build 3 X-15 airframes, while Reaction Motors, Inc. was tasked with developing the powerful XLR-99 liquid-fuel rocket engine, with both companies beginning work on their respective designs in 1956. North American's design for the X-15 incorporated several innovative features tailored to its mission of exploring hypersonic flight and the edge of space. Its fuselage was long, measuring roughly 50 feet in the standard version, and had a cylindrical shape with rear fairings to reduce drag and maintain structural integrity at high speeds and altitudes. The aircraft featured thick dorsal and ventral wedge fin stabilizers, which were essential for maintaining aerodynamic stability and control during hypersonic flight. These stabilizers prevented unwanted yaw and pitch movements, ensuring that the aircraft remained controllable under extreme conditions. The aircraft featured a 13-foot-high, thick, wedge-shaped tail designed to ensure stable flight at hypersonic speeds, although this design created significant base drag at lower speeds, comparable to the drag of an entire F-104 starfighter. This wedge shape was chosen for its superior effectiveness in providing directional stability at hypersonic velocities. To achieve adequate stability, the vertical tail area needed to be 60% of the wing area. It was also equipped with extendable side panels on the tail to further enhance stability at hypersonic speeds. These panels increase the surface area of the tail, aiding in directional control and doubling as air brakes when necessary. What's more, the X-15 carried a sophisticated suite of instruments to gather data on flight dynamics, structural loads, aerodynamic heating, and other critical parameters. This data was crucial for understanding hypersonic flight and informing future aerospace developments. The fuselage's outer skin was made of Inconel X-750, a heat-resistant nickel alloy protecting the X-15 from the extreme temperatures generated during hypersonic flight while safeguarding critical structural components and maintaining durability under thermal and aerodynamic stress. This skin was part of the aircraft's thermal protection system, which also included strategically placed insulation and cooling systems to manage the extreme heat generated during re-entry from the upper atmosphere. The aircraft used a retractable landing gear system with a nose-wheel carriage and 2 rear skids, which were lighter and simpler than traditional wheels. This design contributed to overall weight reduction and provided a reliable landing mechanism suitable for various surfaces. Before landing, the lower ventral fin had to be jettisoned to avoid damage. It had a parachute system in place to recover and reuse the fin. This innovative approach ensured safe landings while maintaining the aircraft's aerodynamic performance during flight. The X-15 was one of the first aircraft to use real-time telemetry, transmitting data back to ground control during flight. This capability allowed for immediate analysis and adjustments, further enhancing the safety and effectiveness of test missions. The X-15's cockpit included various controls and features such as a rocket engine throttle, a control for jettisoning the ventral tail fin, heated windows to prevent icing, and a forward headrest for high deceleration periods. The aircraft had an ejection seat designed for speeds up to Mach 4 and altitudes of 120,000 feet, though it was never used. Pilots wore pressure suits that could be pressurized with nitrogen gas, and above 35,000 feet, the cockpit was pressurized to 3.5 pounds per square inch with nitrogen gas, with oxygen fed separately for breathing. The MH-96 flight control system in the alternative setup allowed for a single joystick that could automatically blend aerodynamic and rocket controls, simplifying pilot input and ensuring effective control of the aircraft under varying conditions. Additionally, the X-15 was equipped with a reaction control system featuring small rocket thrusters on the nose and wings. These thrusters provided control in the thin atmosphere at the edge of space, where traditional aerodynamic control surfaces would be ineffective, allowing for precise maneuvering during the spacecraft-like portions of its flight. One of the other key design choices of the X-15 was the decision to carry the aircraft aloft and drop-launch it from a B-52 mothership. This method was chosen to allow the X-15 to start its flight at a high altitude of about 8.5 miles and a speed of approximately 500 miles per hour, significantly reducing atmospheric drag and aerodynamic heating. This air launch system also enabled more efficient use of fuel and facilitated frequent and diverse testing scenarios, thus accelerating the pace of research and development. Meanwhile, the team at Reaction Motors was hard at work creating the XLR-99 engine, designed to provide an impressive thrust of 57,000 pounds of force, which would enable the X-15 to reach the high speeds and altitudes it aimed for. However, they first decided to test the X-15 with their earlier XLR-11, the engine that had famously powered the Bell X-1, the first aircraft to break the sound barrier in 1947. The X-15, specially configured for flexibility when it came to engines, was initially given a pair of these XLR-11S, which had been enhanced to give a total thrust of 16,000 pounds of force. While this was much lower than the thrust the XLR-99 was being built to deliver, it was still significantly higher than the 6,000 pounds of force that the Bell X-1's single XLR-11 had needed to enable it to fly at supersonic speeds. The early flights of the X-15 program were pivotal in testing and understanding the aircraft's capabilities. The program began at Edwards Air Force Base in California with an unpowered glide flight in the first aircraft, X-15-1, piloted by Scott Crossfield on June 8, 1959. This initial flight involved the X-15 being carried into the sky by its B-52 and released to glide back to the ground, allowing engineers to evaluate its handling without propulsion. On September 17, 1959, Crossfield continued to pioneer the program by piloting the first powered flight, flying the X-15-2 with the XLR-11 engine. Testing with the XLR-11 continued into the following year, but by summer 1960, the XLR-99 was ready to be installed in the X-15. On November 15th that year, Crossfield piloted the first flight using the powerful new engine, which dramatically enhanced the aircraft's performance. In 1961, the X-15 program achieved significant milestones in high-speed and high-altitude flight, with several notable accomplishments. On March 7th, now with pilot Robert White at the controls, the X-15 reached an altitude of 107,800 feet, over 20 miles above ground, demonstrating the aircraft's capability to operate effectively in the thin upper atmosphere. On June 23rd, White further pushed the boundaries by achieving a speed of Mach 5.27 or 3,603 miles per hour, marking the first time a manned aircraft exceeded Mach 5. These flights provided critical data on aerodynamic heating, structural integrity, and control systems at extreme speeds and altitudes. Among the other pilots to fly the X-15 early on was the future first man on the moon, Neil Armstrong, who flew the aircraft 7 times. One particularly notable incident occurred on April 20, 1962, when, while evaluating the MH-96 control system during his 6th flight in the X-15, Armstrong ascended beyond 207,000 feet. He maintained the aircraft's nose elevated during the descent to showcase the MH-96's capability to limit G-forces, causing the X-15 to rise again to approximately 140,000 feet. Traveling at Mach 3 and at an altitude of over 100,000 feet, Armstrong exceeded the landing strip, eventually veering 40 miles south of Edwards. Once at a lower altitude, he maneuvered back toward the landing zone and successfully completed the landing. This flight marked the longest in terms of duration and ground distance covered in the X-15 program. Another landmark occurred on July 17, 1962, when White piloted the X-15 even higher. On this occasion, he reached a dizzying altitude of 314,750 feet, almost 60 miles high. In other words, the edge of space. This impressive feat qualified him for astronaut wings, as well as offering valuable insights into the transition between atmospheric and spaceflight. The following year, pilot Joe Walker went higher still, flying over 328,000 feet or 62 miles above the Earth's surface, crossing the limit that the Fédération Aéronautique Internationale set as the official boundary with space. However, not every test went successfully. On November 9, 1962, pilot Jack McKay encountered an engine malfunction and made an emergency landing at Mud Lake, Nevada. During the landing, the gear gave way, causing the aircraft to overturn and end up inverted. Although McKay recuperated enough to resume flying, his injuries ultimately forced him into retirement. Meanwhile, the damaged X-15-2 was redesigned as X-15A2. This version of the aircraft included several significant upgrades that enhanced its performance and capabilities. The fuselage was extended by 28 inches to accommodate additional fuel, and its overall length was increased by 2.4 feet, improving its aerodynamics. Auxiliary fuel tanks were added beneath the fuselage and wings, further increasing fuel capacity and allowing for longer flight durations and greater distances. A complete heat-resistant ablative coating was applied to protect the aircraft from the intense heat generated at hypersonic speeds. These modifications enabled the X-15A2 to achieve higher speeds and altitudes, extend mission durations, and provide valuable insights into thermal protection technologies. This variation was flown for the first time on June 25, 1964, but its finest hour would come a little over 3 years later, when on October 3, 1967, William J. Pete Knight piloted the X-15A2 to an unprecedented speed of Mach 6.72, or 4,520 miles per hour. This remarkable achievement not only demonstrated the X-15's extraordinary capabilities and pushed the boundaries of what was possible in aviation at the time, but it also set a speed record for a manned aircraft that has not been beaten to this day. A month later, however, tragedy struck. On November 15th, as Major Michael J. Adams performed the 191st X-15 flight in X-15-3, the third prototype, the aircraft went into a hypersonic spin during its descent, followed by intense oscillations due to growing aerodynamic pressures after re-entering the atmosphere. The flight control system of the aircraft maxed out the control surfaces as the acceleration escalated to 15 G0 or 492 feet per second, squared vertically, and 8 G0 or 256 feet per second, squared laterally. The structure of the aircraft disintegrated at an altitude of 60,000 feet, dispersing debris over an area of 50 square miles and claiming Adams' life in the process. Adams would be posthumously awarded Air Force astronaut wings for his final flight, which had reached an altitude of 50.4 miles. In 1991, his name was added to the Astronaut Memorial at the John F. Kennedy Space Center in Florida, and in 2004, a monument was erected in his honor near the cockpit crash site in the Mojave Desert in California. Major Adams's accident would signal the beginning of the end of the X-15 program, as concerns were raised about the risks involved. Moreover, by now, the project had fulfilled its research goals of providing critical data on hypersonic flight and high-altitude conditions. With the X-15 now rapidly becoming obsolete in the face of technological advancements that surpassed its capabilities, attention and funding were redirected to the Apollo moon missions instead. While 9 more flights were successfully completed during late 1967 and 1968, the 200th flight, scheduled for November 21st with Pete Knight at the controls, was delayed 6 times due to a slew of technical issues and unfavorable weather conditions, before eventually being canceled altogether. The X-15 program was officially brought to an end soon afterward. Today, X-15-1 can be found in the National Air and Space Museum in Washington, D.C. in the Milestones of Flight Gallery, though it is currently undergoing restoration work. Meanwhile, X-15A2 is on display in the Research and Development Gallery of the National Museum of the United States Air Force in Dayton, Ohio, alongside other experimental X-planes such as the Bell X-1B and the Douglas X-3 Stiletto. Although the X-15 program lasted less than a decade, it left a significant legacy. The critical aerospace advancements it pioneered, including heat-resistant materials, lifting body aerodynamics, advanced control systems, and insights into human factors, directly informed the development of the space shuttle and other spacecraft technologies, while the project was also instrumental in establishing a framework for pilot safety and aircraft stability at altitudes and speeds previously unexplored. The impact of the X-15 is reflected in every subsequent U.S. manned space endeavor, demonstrating the enduring influence of its technological and scientific contributions.